This is Principles of Ecosystem Ecology, Chapter 14, Changes in the Earth System. At the broadest level, ecosystem ecology has changed the way we view the functioning of the Earth. In this section, we'll review some of the patterns of pools and fluxes of energy and materials at the global level, and examine the changes in the Earth ecosystem that we have caused. Human activities have altered biogeochemical cycles at global scales in ways that change the functioning of Earth as an ecosystem. So we often think about the activities of an individual as being relatively small, but aggregated, they've altered fundamentally how the Earth as an ecosystem functions. But when did this all start? Well, there's been some evidence that even thousands of years ago, when the populations of humans were relatively small on the landscape, the effects that they've had could be seen at the global level. Here's just one example. On the x-axis, I'll have time, and that's in thousands of years. So the present is over here, and we're going thousands of years back, 10,000 years back, 12, 14,000 years back. And on the y-axis, we have methane concentration. And this comes from a Greenland ice core. So bubbles trapped in ice are then analyzed for the concentration of methane in there. And we have a 15,000-year-old record of methane. What you can see is the pattern looks something like this. Methane concentrations were going up, and then they dropped off pretty dramatically. Then they went up again, and then showed a pattern something like this. This pattern, this initial drop-off, could be associated with the extinction of the megafauna. Methane is an important greenhouse gas, and we know that it has a high global warming potential. And we also know that organisms like mastodons and mammoths would have produced a lot of methane. It's been estimated somewhere on the order of 10 teragrams of methane would have been produced annually just in the Americas from the herbivores that were present. Humans caused the extinction of those megafauna, and all of that production of methane would have declined. And it's been estimated that somewhere on the order of 10 to almost maybe even 100% of the decline in methane concentrations that we saw at the global level were caused by the extinction of these animals. The loss of the production ended up with a relatively great decline in methane at the global level. With that would have come a large decrease in the amount of warming that would have occurred and could have even affected global climate. Since then, there's been other patterns to methane, and we'll talk a little bit more about those later, but other things like rice agriculture have been an influence on the global methane concentrations also, as well as a whole bunch of other factors. And we'll talk about those later. But if you want to think about when did this really start to occur, that we can go back into the record 10,000 years ago, 15,000 years ago, and see evidence of biogeochemical impacts at the global level. Now, in general, it's thought of as the Industrial Revolution as being really the time that marks a transition from when humans had a relatively small effect on global scale biogeochemistry to relatively large effects. And there's different industrial revolutions. That first industrial revolution is generally thought of as being from 1760 to 1830. And this is definitely a European view of things, but there are a lot of big changes that were happening during this time period. And among those really was a shift to coal. That once coal started to be mined, that had big effects on atmospheric chemistry. And we can see that shift to coal in changes in atmospheric carbon dioxide concentrations as well as NOx. So, of those factors that happened during that first industrial revolution, mining was a really big one, and it started to change global biogeochemistry. But also that increase in agriculture that happened there too. And we'll look at changes in population levels that happened and changes in the way that humans interacted with their landscape. The authors offer a focal issue for this chapter, just like in previous chapters, and they say that the aggregate effects of human activities have altered biogeochemical cycles at global scales. Carbon dioxide concentrations have increased by 35% since the Industrial Revolution. Now it's probably even closer to 40%. And with the CO2 concentrations going up in the atmosphere, CO2 concentrations have also gone up in the ocean, and that's actually increased ocean acidity. When we look at the ocean, that there's a lot of biogeochemistry that happens, especially with carbon. And coral reefs are important parts of the oceans. They're hotspots of diversity. They're important for a lot of other factors besides just holding a lot of animals. They provide important food resources and storm protection also. They're breaks against the waves. So corals are important. But corals, they require carbonates in the water in order to form their structures. And carbonic acid is a byproduct of CO2 being dissolved in water. So CO2 plus water gives you carbonic acid. And increasing the CO2 concentration in the water increases the acidity. And as a consequence, it makes calcium more soluble. So calcium carbonate is a lot less soluble at high pH and becomes more soluble at low pH. And as we increase the acidity, calcium carbonate dissolves more in water. And calcium carbonate is the backbone of a lot of those structures for some things like coral. So when we think about that focal issue, we'll say, what are the potential consequences of altering the food base of the world's oceans? A lot of the food base of the world's oceans really requires calcium carbonate structures. And simply by changing the pH of the oceans, that there's potentially large ramifications to one of the more productive portions of our biosphere. How might changes in ocean productivity feed back to affect the CO2 concentration and climate of the Earth? So it's one thing to say that by increasing CO2 concentrations in the waters, there's going to be changes in productivity. But we also have to understand what those feedbacks might be. And it might become an amplifying feedback to CO2 concentrations and temperatures. I also think it's important not only to think about the oceans, but for a focal issue and really for terrestrial ecosystem ecology, is to ask how are increased CO2 concentrations altering terrestrial productivity? And that has been just as an important question as the ocean productivity. And lastly, how are increased CO2 concentrations altering nutrient cycling? We know that nutrients are limiting on a global scale, and if increasing CO2 concentrations indirectly or directly are going to increase nutrient availability, that's going to change the productivity of the terrestrial biosphere. If increasing CO2 concentrations actually reduces nutrient availability, then that could be a situation where that would reduce the amount of carbon dioxide that can be taken up by the land and really serve as an amplifying feedback to CO2 concentrations in the atmosphere. So understanding how CO2 affects productivity in the ocean as well as the terrestrial biosphere becomes a focal issue for understanding the biogeochemistry of the Earth system.